This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hi everybody, good afternoon. And today we're going to continue talking about dimensionality reduction techniques. And just to start, let's just have a brief recap of what we discussed last lecture. So we previously started talking about dimensionality reduction and why do we need it. We introduced one algorithm for feature selection, which is stepwise backward and forward greedy feature selection, and we mainly focus on two feature extraction algorithms, principal component analysis and singular value decomposition. Today we're going to focus on four new algorithms, new feature extraction algorithms. The first one is MDS, multidimensional scaling. We'll also talk about isometric feature mapping, isomath. And also we're going to talk about stochastic neighbor embedding, TSNE. And we'll finish by talking about a fairly new algorithm called UMAP. And most of these are not focused on reducing noise, but rather different techniques to facilitate the data visualization and analysis. So just as a brief recap of what we discussed on Wednesday, so why do we need dimensionality reduction? So we've been generating a lot of data over the years, and with that we have a lot of dimensionality, a lot of interesting data to analyze, but that comes with a cost associated, and that cost has basically three flavors and three issues. The first one is with dimensionality, with high dimensionality data, it comes an inherent difficulty in data interpretation and visualization. And that's basically because we can only see 3 dimensions. But also, with high dimensionality comes noise. And at some point, we will start adding information that is either redundant, for instance, features that are related to each other, they are correlated, or features that are irrelevant to model the problem we want. And as an effect, this will probably degrade machine learning algorithms if we plan to use them. And also, but not less important, computational costs. So if we have more features to analyze, that will therefore affect all the cascades of algorithms we need down the track. And we also mentioned something that comes with dimensionality, which is the curse of dimensionality. And it basically implies that if we want to model properly a function, the number of examples we need grows exponentially with the number of dimensions we add. And with that, we will have a theoretical maximum number of features above which the performance of predictive algorithms will degrade. We'll have something like that. And the way to overcome the curse of dimensionality is, of course, reducing dimensions and throwing away things that are not relevant or not important. And the basic assumption of that is that most of the variation is often in a small subset of data. So our true structure of the data is hopefully in a smaller manifold. And we discussed about 2 main approaches for dimensionality reduction. The first one was feature selection, which basically out of our complete set of features we are evaluating, we will choose a subset of those based on different criteria and different objective functions. And the other alternative is feature extraction, which is basically we're going to create new features based on existing ones. And so far, we talked about linear feature extraction. So we will do a linear combination of the previous features to generate a new dimensional space. Okay? And in either case, the main goal is to find a low-dimensional representation of the data, reducing noise and assisting data visualization and analysis. And we focus on 2 linear component ones, linear projection algorithms, PCA and SVD. With PCA, we just want to find orthogonal vectors that we call components to represent as much variance as possible in the data. So alternatively, what we can interpret as PCA is trying to identify a line. Let's say here we have our 2D data. We want to find a line that maximizes variance, and alternatively, we want to find a line that minimizes the projection error in the data. So there are many opportunities there, but this one is actually the one that minimizes projection data and maximizes the variance that is represented in that variable. And PCA then is calculated by decomposing our covariance matrix C into eigenvectors and eigenvalues, which will be ordered by importance or by how much variance is explained. And alternatively, we can also use a sister technique, which is called SVD, singular value decomposition, which is more efficient. Why is SVD more efficient than PCA? What's your name? You don't know? Okay. Why is SVD more efficient than PCA? They're very similar techniques, but yeah, you don't need to calculate basically the covariance matrix, which is a quadratic cost. So SVD is an alternative that is more efficient, and you can interpret PCA as an SVD on a centered covariance matrix, okay? So the first method I'd like to introduce today is called multidimensional scaling, or MDS. And this is, again, a feature extraction method. Therefore, we are not selecting a subset of features. Rather, we are combining existing features into new ones. And it calculates, given a matrix of distances between features or dissimilarities. And what we want, MDS, you want a lower dimensional representation that best preserves the pairwise distances between our features. So this is mainly a feature visualization technique. So it's not a learning algorithm. It's a very descriptive technique that has been more useful for visualizing data and interpreting data rather than removing noise. And the main goal then is going from a similarity or dissimilarity matrix and try to represent the distances in the similarity matrix in a lower dimensional space, either 2D or 3D. So usually with MDS, we want to plot a graph, either in 2D or 3D. And there are several applications, but the main one is indeed data visualization. MDS is also called principal coordinate analysis, not to confuse with principal component analysis, okay? The goal here is then to preserve as much of the pairwise distance in high dimension, while PCA, we want to describe as much variance as possible, okay? So, as mentioned, multi-dimensional scaling requires a pairwise distance measurement between points, and for that we can use our good old distance matrix or dissimilarity matrix. And let's say in that case, we have a toy example of 3 samples in 3-dimensional space. So let's consider we always have 3 features in this case. And here we have 3 samples, A, B, and C. And first thing we do, we calculate the distance matrix between them. And let's say A, B, and C are equidistant in space, in 3D space. Okay, so distance from A to B, A to C, and B to C are equal, and let's say they're equal to 1. And the question here is, how do we represent this in a lower dimensional space? So from 3D to 2D. And in that case, we can represent exactly those distances in 2D, basically by plotting a triangle. So distance from A to B, B to C, and C to A are all 1. So we have 3 samples plotting in 2D. We can represent them exactly. Let's say we have 4 samples, also in 3D. And let's say we also generated this dissimilarity matrix or similarity matrix. And again, they are all equidistant. So 4 points in 3D, so 4 points in space that are equidistant, we can plot them as a tetrahedron, okay, a pyramid. But that meaning that 4 points require 4 minus 1, so 3 dimensions to plot and to preserve all the distances. Meaning we do need a 3rd dimension to draw it exactly. And actually, the best we can do in 2D is something like this. So let's say we put A in the middle, and we have B, D, and C. And you can see this is just an approximation. So the distance between A and B is smaller than D to D. But that's the best we can do in 2D, which is just a projection. So MDS is not a perfect technique. And in fact, in general, if you have n samples, exact pairwise distance representation will require n minus 1 dimensions. That's not the case. For MDS, we are interested in going from a high-dimensional space from either 2D or 3D for plotting. And therefore, the MDS formulation is as follows. So we want to preserve the original distance as much as we can. Of course, this is approximation. It won't be perfect, but we want to preserve the original distances between points in high dimensional in as much as possible. And multidimensional scale is actually a family of different algorithms. And it's designed to arrive at a low-dimensional data representation, usually 2D or 3D. And then on multidimensional scale, what we have is an objective function that will measure the distortion from the original to the modified distance. So how close are the modified distance on our 2D or 3D projection in comparison to our original high-dimensional distances? And so what we basically need to do is find a projection. How do we find a projection? It's similar to what we did with PCA. We find a vector from which we can then project our data, either in 2D or 3D, 2 or 3 vectors. And what we need to do is select the vectors that minimizes or maximizes this objective function. So that's how we carry multidimensional scale. And for that, usually it's used a metric called stress, which is also known as lack of fit measure. And what it means is higher values, higher stress indicates poorer fit. So there's a high difference between the high dimensional distance and low dimensional distances. And these will tell us how well lower dimensional distances represent the original ones. And an interesting thing about multidimensional scaling is that it uses pairwise dissimilarities that can be used then to visualize data, even when the dissimilarity is not Euclidean. So, for instance, in Euclidean space, if you think about, let's say, a sphere in three-dimensional space, and you have one point in the surface of the sphere, and you have a second point on the opposite side of the same sphere. What's the Euclidean distance between these 2 points? It's the diameter of the sphere, okay? So what multi-dimensional scale will let you do is consider other types of distance. For instance, the distance in the surface of the sphere. Instead of the diameter, it will be, for instance, the half of the circumference, which is pi times r. Okay, so it lets you deal with data that is not necessarily based on Euclidean distance. For instance, it's easier then to perceive and model similarities between colors, between countries' economies, similarities between DNAs and protein sequences. And for visualization, we bring those similarities into 2D or 3D Euclidean distances, and then we plot them, okay? Because that's our space is Euclidean. So as I mentioned, a multi-dimensional scaling defines a class of algorithms, and there are basically 3 classes, and they're very similar. And the first one is a metric MDS, and a metric MDS, as I mentioned, it will try to minimize a stress function. It's the lack of fit measurement. And basically, a metric MDS will try to preserve the distances between, let's say, our vectors xi and xj that represent our points in high-dimensional space, so points I and j in high-dimensional space. So it will try to minimize the stress, minimize the differences in those distances. And that can be done using a cost function. For instance, I want to minimize the difference in the distance between these 2 points in high dimension and lower dimension. Okay? In that way, then, distances are used as a quantitative measurement. The non-metric MDS, on the other hand, will try to maintain the original ranking of the pairwise distances, even though the magnitude could vary. So if we have that A is closer to B than to C, that order needs to be maintained for non-metric MDS, but not necessarily the same proportion. So distances for non-metric are taken into consideration as qualitative only, okay? And there's also the generalized MDS that we're not going to approach, which is basically mapping from one surface to the other. So distance-based MDS, which is the most common algorithm. So it starts with a distance matrix or a dissimilarity matrix and a k-dimensional metric space to embed with. It is either a 2D or a 3D space. And what we want to do is to minimize the stress, which is our objective function. And there are different ways to optimize a given function. So stress is basically the error in the distance. Compare the distance between 2 points in high dimension and low dimension space. And it can be given, for instance, as a given expression. Stress could be basically the difference between my distance in high dimension and the distance in lower dimension, considering Zi and Zj, the mapped points in k-dimensional space. Okay? And we want to minimize this function. And even though the actual stress used may be more complex, for instance, they could be normalized distance, weighted distance, and so on and so forth. But the minimization process will follow in the same way. And the most simplest way to do this function minimization, and is the most commonly implemented, is using an algorithm called gradient descent on the objective function, where the object function is the stress. So the difference between the distance in high space, high dimensional space, and low dimensional space. And basically, gradient descent is a class of algorithms where we iteratively try to improve a solution to either minimize or maximize it. So the basic approach for gradient descent is, as a given step, we will find a derivative of the curve. You can think about gradient descent this is basically our search space, where we have different values for our objective function. Ideally, I would like to get to a global minimum. And what gradient descent does is finding a derivative, which, for instance, it could be the slope of a curve. That's the highest derivative. And we adjust the parameters to go in the direction of the steepest descent, like walking down a hill, proportionally to the slope. So if it's more inclined, we go faster. As it gets flattening out, we stop, basically, until it reaches convergence. And the problem is, one way to implement gradient descent is stochastically, and it not always guarantees that convergence is achieved, nor the minimum. So sometimes you can go to local minimum, okay? Especially if the objective function is complex, we could end up in just a local minimum instead of the global one. But we will end up with a 2D or 3D representation of the data that we can plot and analyze and see if we can find interesting patterns, interesting clusters, but we need to pay attention on how to interpret low-dimensional visualization for this type of technique. For instance, the exact positions on a plot for MDS, they're not that useful. So if this plot is like this, or upside down, or multiplied by -1, that doesn't matter. So this point being up here or down here, it doesn't matter. So it doesn't have an inherent meaning to it. However, the clusters, they usually represent real clusters. And also outliers in that case is also represent real outliers. And one important thing here is the two new dimensions, they are not ordered by importance or variance like we have in PCA or in SVD. Our goal here is just to retain as much as we can in terms of the distances. And also, however, the ordering along an axis may represent a real ordering, but not the actual dimension. So it's difficult to interpret the actual dimension. And one important difference from PCA and SVD, we can't reconstruct or approximate the original data using this. This is not for noise removal, it's mainly for data visualization. Okay? And that's 1 out of 4 algorithms. The second one, it's a nonlinear one. So far we've been talking about linear projections of the data, so linear-based feature extraction approaches. ISOMAP is a nonlinear one. So what happens is, a lot of the time our data lies on or near a nonlinear low-dimensional surface, and this is usually called a manifold, so a given arbitrary surface. For instance, if our data looks like this, it's called Swiss row data, and it might be more meaningful to describe the distances considering this manifold, so considering the distance in a 2D plane rather than in 3D. So this is saying that the actual true structure of the data, it's not three-dimensional, it's two-dimensional. So when we have data like this, we can use, for instance, ISOMAP to better understand it in lower dimensions. So ISOMAP stands for isometric feature mapping, and it's been quite well used over the years. It was published on a science paper in early 2000. It has more than 12,000 citations, so it's very well used. It's a non-linear method for dimensionality reduction, and it tries to preserve the global geometry of the data by preserving, instead of the actual distances, preserving geodesic distances. We already talked about this. Does anyone know what geodesic distance means? We used a different term. So geodesic, originally geodesic means the shortest route between 2 points on a given surface of the manifold. In a graph, a geodesic is basically the shortest path between 2 nodes I and j. Okay? So we're basically are going to model our data into a graph. And it does as follows. So ISOMAP, first thing, we'll try to model the geodesic distance between points with respect to our manifold. This, for instance, is a Swiss roll data. And we'll try to estimate the manifold using a graph. So we'll compute the distances between points as the distances in a shortest path, all pairs shortest path in a graph modeling of our data. And what we're going to try to do is embed this graph into 2D and use Euclidean distances to approximate the actual graph distance. For instance, in blue here, we have Euclidean distance into D. In red, the actual shortest path in the graph. So there are basically 2 steps to ISOMAP. The first one is actually calculating the geodesic distance between every pair of points in our graph. And Euclidean distances, they usually work well if the points are close enough. For instance, these 2 points are connected, so we can consider the distance between them as the actual Euclidean distance. And for points that are far apart, the geodesic can be estimated by summing up local distances between hops in the path. And then what we need to do is define an Euclidean mapping from the graph distances to an actually Euclidean distance, preserving the actual geodesic distance. Okay? So geodesic distance is a non-linear, non-Euclidean distance. We want to then find an Euclidean mapping to 2D, for instance. So first thing we need to do is to construct a graph. So we have our data in n dimensions, and we'll connect to data points I and j if they're close enough. So this is called epsilon isomap. So if the distance between any 2 points in our data set is closer than a given threshold, we'll say it's connected. Or alternatively, we can say that if I is on a j's k nearest neighbors, we then connect it. So this alternatively is called k-isomap. So we have 2 approaches. One, we define a minimum cutoff distance, and the other one, we say we're going to connect all our k nearest neighbors. And we also set the edge weights to actual Euclidean distances. So this is a weighted graph, a simple graph, since there is only one connection between any 2 nodes, and an undirected graph as well. And then what we need to do is to compute the geodesic distance between all pairs of nodes in the graph, which are the shortest path. And there are different algorithms to do that. Dijkstra, for instance, which is a modification of the breadth first search. So since we have our graph, so we have defined our graph, what we need to do is, with our graph, we'll have all pairs shortest path, which is basically a distance matrix between all the nodes in the graph. What we need to do is then to compute a low dimensionality mapping from that distance matrix. And what we can do then is basically use multidimensional scale to then convert this to 2D. And that's possible because we'll have then n by n matrix, which is our distance matrix. And as an output, we'll have a coordinate configuration in low dimensionality space, usually for MDS, either in 2D or 3D. And this will be as closely as possible to the geodesic distances. And ISOMAP has been used in a different sets of scenarios. For instance, in discovering intrinsic manifolds in images. For instance, this is a set of images of faces, and they are either facing up or down, left or right, and they have different lighting directions. And what ISOMAP manages to identify different sets of different images, either facing up or down, facing left or facing right with different lighting. So it manages to actually decompose the data into real clusters, which is quite interesting. And this going from over 4,000 dimensions to 2, which is quite powerful. So a third algorithm, which is an evolution of these two, is a stochastic neighbor embedding, which is based on student t-distribution. Therefore, it's called t-distributed stochastic neighbor embedding, TSNE. And this method, on the other hand, will try to preserve the local structure of our data instead of the global one, like PCA tries to do. So PCA tries to do is represent as much variability as possible. That's considering the whole data sets. So that's a global preservation, while TSNE tries to preserve the local structure. And it does that via a probabilistic version of multidimensional scaling. So stochastic neighbor embedding has a probabilistic way to decide whether two pairs of nodes, a pairwise distance, is either local or not. And then it converts Euclidean distances to probabilities. So there's a probability to say that two given nodes are local, are connected or not, and this is proportional or inversely proportional to their distances. And it does that basically by modeling the probability, the conditional probability of J being local to I, modeling it as a Gaussian. And each point in high dimensionality has then a conditional probability of picking another as a neighbor. So this is a completely stochastic method. Therefore, if you run it different times, you end up with different results. And this is basically the probability of picking J given you started with I and calling it as your neighbor. And interesting thing about stochastic neighbor embedding is once you have all the probabilities calculated and then you have your probability matrix, you don't need to look at your high dimensional space anymore. You can throw it away. And the next thing you need to do is once you have your dissimilarity matrix, you then need to calculate and evaluate what's the best mapping, what's the best projection either in 2D or 3D to choose based on that dissimilarity matrix. And then for that, you need to evaluate how good it is. So for MDS, we have an objective function. For this, we also have an objective function, which is a new function, Qij, which is in lower dimensional space. So once we reduce it to either 2D or 3D, we will define this. And it's basically, the difference here is that the Q is based on a student t distribution instead of a Gaussian. And the main reason for that is that the probability of students t goes to 0 much is lower than the Gaussian. So we have a Gaussian here in green, and we have two student t's here in yellow and blue. And what we can see, for instance, in the blue is that the student t usually have a heavier tail than the Gaussian. And the effect that this has is basically relaxing the distances of points in space and avoiding overcrowding points when we do our 2D or 3D representation. So making the points a bit further away from each other. Okay? So similarly, then to optimize this function, stochastic neighbor embedding will do a gradient descent algorithm on this cost function. And the difference is that the cost function is between two probabilities instead of two distances. So the cost function in this case is a measure of the difference between the high dimensional probability, P, and the low dimensional probability distribution, Q. Since this is not a distance, this is probability, there's also a metric for this, which is called Kullback-Leibler divergence. So you don't need to worry about this formula. But since it's comparing two probabilities, that's a standard way to assess how divergent two probability distributions are. Okay? So instead of assessing the cost, the difference between two distances in this case, stochastic neighbor embedding will compare the divergence between the two probability distributions of the points. And if you compare the two, and people have been comparing these, for instance, with images, and one example is this MNIST data sets, which is a very classic machine learning data set of images of handwritten digits from 0 to 9. And while isomap doesn't make a good job of separating them, stochastic neighbor joining managed to actually plot them properly into dimensional space. This is also available, and so is the publication and the code for TS and E, so this assures reproducibility as well. And the final algorithm is called UMAP, which stands for Uniform Manifold Approximation and Projection. It's a fairly recent one. This was published last year and already has 300 citations. So it's been very, very well used. And it's a method that it's inspired in the stochastic neighbor embedding, but it's based on manifolds and topology rather than probability, and it's considerably quicker than that. So we will not look into the math for this method. It's fairly complicated, but the publication and the code is also available. I also recommend 2 talks about this method, which is in SciPy and PyData as well. And basically, the intuition behind UMAP can also be seen as a graph method, similar to isomap. So in the first phase of the algorithm, we need to define and construct our graph. And in this case, we wanted a weighted k-neighbor graph. So instead of saying we want a cutoff of epsilon and define everybody that is within that cutoff connected, we will consider k-neighbors. This is an input parameter in the same way that for isomap, the k or the epsilon also is an input parameter. And then we construct our graph. And in the second phase, we will try to find a low-dimensional layout of this graph. Instead of finding an Euclidean representation of the graph, we will just try to represent the graph in 2D. And this is done via force-directed graph layouts. So that's the main difference between isomap and UMAP. And basically, with the weights in the edges, what it does is it tries to attract points nearby, saying that using this force directed, so points that are close together, they'll tend to get closer. And also, it's done a edge-weighted normalization globally to force pushing points apart as well, as they are getting closer. And the algorithm basically iteratively apply attractive and repulsive forces at each node, okay? And if you compare stochastic neighbor embedding with UMAP, you usually have better, well-defined clusters on UMAP, basically because it's trying to use this force-directed graph, and it's also considerably quicker. And this has been used also on a image data sets, in this case are fashion items instead of handwritten numbers. Each item then is categorized. This is also available, and they also compared with PCA. And PCA, even though it does do a reasonable job at separating the different items, if you compare with stochastic neighbor embedding, it does a considerably better job, and UMAP does an even better job with the following advantage. So UMAP is at least an order of magnitude faster than stochastic neighbor embedding. And also, UMAP is deterministic, meaning every time you run it, you get the same result. If you run T, S, and E 10 times, you get 10 different results, 10 different plots. So it's basically on the name, it's called stochastic, okay? So that's one of the drawbacks of the stochastic neighbor embedding. And also, UMAP can use the labels you provide to actually guide the dimensionality reduction in the way the clusters are put together. And there is also very, very fast and parallel implementation in Python. So this is all for dimensionality reduction. Just a couple announcements before everybody runs and enjoys the weekend. Assignment 2 will be released on Wednesday, okay? And just a reminder, next Friday we will not have lectures nor tutorials. This has been rescheduled for the week after the mid-semester break, okay? Thank you very much. Oh no, I have closing thoughts, never mind. No, I have closing thoughts. No, I forgot about this, sorry. So don't run. Two things you need to be very careful with all these methods. So they are not for noise removal. They are just for plotting data and interpreting them and identifying clusters in your data. So the distances, they don't mean anything, okay? So if you see 2 points here, you can't use that as a metric to say how distant they are. This is just arranging data neatly in 2D. The other thing is the dimensions have no interpretable meaning whatsoever, okay? This axis and this axis, we have no idea what it is. It doesn't have an inherent interpretation compared to PCA. So in PCA, we can say what's the contribution of the features for each of the components, not here. So this is basically focused on visualization. And also, these techniques, especially stochastic neighbor embedding and UMAP, they all have parameters you need to set. And you need to be very careful how you set them, otherwise this will have a huge impact on your results. But they are very powerful tools for visualization. These are the cutting edge tools. Okay, now we're done. Thank you very much.